Hey guys, this video is about absolute value functions.
It's nice to see students so excited about math. So absolute value functions, what they are, let's start off with just what is an absolute value. So absolute value just refers to the positive value of an expression. So for example, the absolute value of 7 is just the positive value of 7, which just comes out to 7. Easy. The absolute value of negative 50 is just the positive value. So we just basically sort of take away that negative sign. So it's going to just be 50. The absolute value of 0, what do you think that's going to be? Well, 0 is not really negative or positive. So the absolute value is just going to remain as 0. And then to evaluate this expression here, the absolute value of 5 minus the absolute value of negative 9 plus 3 times the absolute value of 5 minus 12. Again, let's just sort of evaluate that. You can sort of think of them as brackets, right? They're brackets that have a special property, in which case that just means they're making it sort of positive. So 5, the absolute value of 5 is 5, minus the absolute value of 9 is just 9, plus 3 times the absolute value of 5 minus 12. Well, 5 minus 12 is 7, negative 7, but we're going to make it positive because that's what the absolute value does. So this function basically evaluates to 17. Sorry, I need to go grab my calculator to find that answer. So there's actually one more thing, one more way to look at what the absolute value function is. This is really what it actually is. We say it's when it turns a negative value positive and keeps positive values positive. But another way to think about this is if we think about a number line. So let's take this negative 50 example right over here, right? Let's just draw a little number line. We have 0 here. We have negative 50 over here. Another way to think of absolute value is just how far we are away from 0. So in this case, 50 or negative 50 is 50 units away from 0. So we don't really care about the sign when we're looking for the distance between two things, right? So we're basically just finding the positive value, which is the distance between that. So same thing with positive 50. Well, the distance between 0 and positive 50 is also just 50, right? So we can also think of it as the distance a value is from 0. So what does the graph of an absolute value function look like? Let's start off by doing just a quick table of values to see what it's going to look like. If we have x and f of x here for just the absolute value of x, and we'll go from negative 2 to 2. So negative 2, negative 1, 0, 1, 2. Well, the absolute value of that, of negative 2, is just going to be 2. The absolute value of negative 1 is 1, 0, 1, 2. So to graph that, just table of values, we can just plot our values there, 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 and there, right? So we have this positive part here and this negative part here. It's sort of like it's got a positive branch here, and then it's got a pointy part at the bottom, and then it goes up on the negative side. And it sort of looks like it reflects off that x-axis. So that's what our sort of parent function for a absolute value function looks like. Now, what does the second one look like? X squared minus 1. So this one's a little bit more complicated. Again, we're just going to make a table of values here. Right? Actually, you know what? We're not going to make a table of values. Let's start off by just sketching what x squared minus 1 looks like. Let's call this g of x. Let's pretend, minus 1. Let's pretend that the absolute value function isn't there. What would this look like? Well, it's just a parabola, the base parabola that's shifted down by a factor of 1. So it's going to look something like this, right? So we'll call that g of x, okay? Remember, what does our absolute value function actually do, the absolute value applied to that? It turns all the negative values positive, right? So if you think about it, I'm just going to zoom in here. It's going to turn, is it going to change anything over here? No, because all those values are positive, right? It's going to keep them positive. Same thing over here. It's going to keep those values positive. By the way, I didn't draw this very nicely. It should go through that point of 1, 1. Anyways, what's it going to do, though, to the values of over here? Well, think about this one critical point down here, this 0, negative 1. It's going to basically turn that negative 1 into a positive 1. right? Because it's going to turn the negative value positive. And it's going to do that for every value between as well. So really, it's going to make the graph look something like this red line here. What it sort of looks like is it bounces off of the x-axis. The function sort of bounces when it gets to the x-axis, and it reflects just the part that's below the axis. So some of the properties of absolute value functions, the absolute value of 0 is 0. The absolute value is never negative, right? So whatever comes out of the absolute value function is always positive. And another way to think about it is it's the distance of any number x is away from the origin. Now we can think of the absolute value function, the parent absolute value function, as actually a piecewise function, which we did in the last lesson, right? So we can think of it like this. There's a piece if x is greater than 0, and that's just the equation of that is going to be positive x. And this is what we see in our graph over here, right? See how this part of the graph, this equation, this part has just an equation of x. It's a positive slope of 1 and a y-intercept of 0. But when x is less than 0, it's like the slope switched around, right? So that the equation of the graph is negative x when x is less than 0. So this is sort of our definition of an absolute value function based on, or made to look like a piecewise function. So let's solve some equations with absolute values in them. The first one, the absolute value of x minus 3 equals 4. Well, our first instinct might just be to solve this like a regular equation, and we can, right? I'm going to move that 3 to the other side, and it's going to become a 7, right? 4 plus 3 is 7. So what's the solution to this? So let's just think about it logically first. What values that we plug in for x are going to give us 7? Obviously, if I plug in x as 7, that's going to be a solution, right? Because just plugging in 7 is going to equal 7. But is there another solution to this problem that can give us 7? What if we plug in the negative version of that? What if we plug in negative 7? What's the absolute value do to that? Well, it's going to turn it into positive 7. So negative 7 is another number that we plug in here. It's going to give us the correct answer. So there actually are 2 solutions to this problem because of that. Now, if you want to see what's happening graphically, I think this is a good way to illustrate it. We can just draw a quick sketch of the graph. So let's just do the left side and right side like we usually do. What's happening on the left side? Absolute value of x minus 3. Well, that's just saying like your regular absolute value function, but shifted down by a factor of 3, right? So it's going to end up down here at 3. And this is going to be the absolute value of x minus 3. And it's saying, where does that intersect with the line 4? Right? So this is up here at 4. Not to scale, but that's okay. So what are our points of intersection of these two things? And we see we not only have this positive root over here at 7, but we also have the negative root over here at negative 7. So another way of solving this would be to look at the left side and the right side as 2 separate lines that are going to intersect with that. And we'll see how to do that in the next question that's a little bit more complicated. So here we go. 3 absolute value of 5x minus 7x. Oh, this should actually read 5x minus 7. Let's get rid of that x there. Equals 15. So let's start by solving it like a regular function. Let's isolate that absolute value first to make it a little bit easier to work with. So let's get rid of that 3. So just the absolute value of 5x minus 7 is equal to 5. Okay, not too bad. Now we're sort of stuck. Because if we solve it like a regular equation, we're only going to get one answer. If we sort of ignore that absolute value and solve it, we're going to get one answer. And that is one of our answers. But we know an absolute value function might have more than one answer because the absolute value has more than one branch, right? So essentially what we're saying is there's 2 separate functions here. There's the positive side and the negative side. And in order to solve these, I like to actually break it up into those 2 separate functions. So to look at those 2 separate functions, let's talk about the positive side first. If this whole thing inside the brackets is positive, the function is just going to look like the regular function. And this happens basically when this is positive, right? So it's like when 5x minus 7 is greater than 0, right? We're going to have this positive case because that's sort of when the thing in the absolute value evaluates to a positive number. When that's the case, we are going to have basically our regular function. 5x minus 7 is equal to 5, right? and we can solve that function pretty easily. So that's going to come out to 12, 5x. So x is just going to equal 2.4. So that's the answer to the positive side of this. But what happens if this thing in the brackets, or in the absolute value, is negative? So that happens when 5x minus 7 is less than 0, right? When that thing is negative. Well, we're going to have that second branch of the absolute value function, right? Think of it. We have an absolute value function with a positive branch and a negative branch, and we're finding where that intersects with a line. So this is essentially looking at that negative branch. So that, in order to satisfy that, we can basically look at this as the negative version of this function, 5x minus 7, because the negative version is also going to be plugged in and give us the same value. So we can solve this equation in the same way. Negative 5x plus 7, if I distribute that negative in, is equal to 5. And solving this equation is going to give me something slightly different, right? It's going to give me, this is a negative 2, negative 5x. So x equals 0.4. So that's where this function intersects on this negative side at an x value of 0.4. So there we go. We have our solutions. Now, there is one last thing we have to do before calling it a day. We have to check to make sure both of these solutions actually work, because we found a solution for this, right? But we need to make sure that 2.4 actually satisfies this inequality, because there is a possibility. Remember, this side of the equation refers to this line here, right? But there's nothing in the algebra that doesn't prevent this line from continuing on forever. So for example, what if our graph, instead of looking like that, we don't actually know because we haven't graphed this thing. What if it looks like this? What if our absolute value function looks something like this? And it's saying, where does it intersect with this line here? Now, it looks like there's no solution to this problem, and there is no solution to this problem. But the thing is, this branch here, when we're solving it algebraically, we're not actually limiting that branch, right? Essentially, what it could happen is that this line could be continuing on like this. There's nothing in the algebra to prevent that. And same thing on the negative branch. The negative branch is just the equation of a line. Like this equation here is just the equation of a line. So we're saying it could continue down like that. So if we did all this algebra, we could actually be finding these sort of phantom zeros that doesn't actually exist. So the way we can check if we found correct solutions or incorrect solutions is just by checking to see if these x values satisfy this. Because this equation is only true when 5x minus 7 is less than 0. So let's check. Let's check the first one. So if I plug in, so I'll call this the check, I can plug this in. 5 times 2.4 minus 7 is greater than 0. If I solve that, if I just plug in the values, 5 times 2.4 minus 7, that's going to give me 5. Is that greater than 0? It is. So we actually are intersecting along this branch. It's actually intersecting with a point out here because we are in the correct range. Same thing for the second one. Let's check that. So 5 times 0.4 minus 7 is greater than 0. Is that true? 5 times 0.4 minus 7, that gives us negative 5, which is less than 0. So it means that these two solutions are correct. We have intersected at some point here and some point here. There we go. So whenever you solve these inequalities, if you're not graphing it out accurately, you always need to check to see if your solutions fall within the right ranges and you're not finding these phantom solutions that we illustrated here. So here we go, on to the next one. Same idea. So let's isolate the absolute value function first. So I can do that just by dividing by 2. So absolute value of x plus 5 is equal to negative 2x. Now that I have that absolute value function isolated, we know there's going to be multiple possible solutions, right? When this thing is positive, it's going to give us one solution, and when this thing is negative, it's going to give us another solution. So we're going to break up this thing into two cases, where x plus 5 is greater than 0, the positive solution, and when x plus 5 is less than 0, the negative solution, right? So in the positive solution, the thing inside the bracket is going to be positive, so it's just like saying positive x plus 5 is equal to negative 2x. And in the negative case, it's like saying negative x plus 5 is going to equal negative 2x. And these are just two equations we can solve very easily, right? So if I solve this, left side is going to be 3x equals negative 5. So x is going to equal let's just keep it as a fraction, negative 5/3. And then on this side, if we solve this one, well, that's going to be negative x minus 5 equals negative 2x. So that, if I solve that one, that's going to be x equals 5. Solving that pretty easily, x equals 5. So we have our two solutions, possible solutions. So again, we need to check to see if this branch actually intersects with this line, and if this branch actually intersects with this line by checking our conditions, right? So let's do our little check. Our check. Does negative 5/3 plus 5, is that greater than 0? Well, I can usually just plug that into my calculator. 5/3 plus 5, that gives us 3.33. That is greater than 0, so this is a solution. And we can check this one as well. 5 plus 5 is less than 0. Is that true? Is it? Definitely not, right? 10 is not less than 0. So this is not a solution. Now you still might be a little bit confused about why that's not a solution. So what I'm going to do is I'm actually going to throw this into Desmos so I can show you very clearly why that is not a solution to the problem. So there we go. I plugged in our function, the left side and the right side of the original function, right? And you can see, so the red line is the absolute value part of it, and the blue line is just that negative 4x. You can see that there definitely is a point of intersection at what looks to be negative 5/3, which is about negative 1.6. Right? So that's true. Now, this other solution of 5, clearly, if we're looking at the graph, clearly it doesn't the blue line doesn't intersect that red line anywhere else, right? If we zoom out, that blue line is actually getting further away from it as we go up to the left. So there's no solution at this 5. So what did we actually find? Where did that 5 actually come from? Well, remember, that came from the negative branch, and the negative branch is this part right here. Right? So essentially what we found is we found the intersection of this negative branch with the blue line. And will that negative branch ever touch the blue line? If we continued it down here, yes, it would, right? It would intersect somewhere down here. And I can show that to you very clearly if I just plug in that negative branch. The negative branch was negative x plus 5, x plus 5, oh, actually, not negative x plus 5. Since we graphed the original function, what I'm finding is actually the negative of the original function, right? So it's going to be negative 2x plus 5. And I'll put that in brackets, x plus 5. Plus 5. There we go. And close our brackets so it's proper. And I'm actually going to change that if I'm able to on here. I think I'm able to. Can I change that to a dotted line? Oh, maybe not. That's okay. There it is. Sorry about that. Desmos is a little bit finicky on this explain everything out. Anyways, so you can see the green line represents that negative branch, right? And that negative branch, if we were to continue it, goes down here and actually does meet up with the function at negative 5. So there is actually a point of intersection between that negative branch and the line, but the negative branch is actually limited to this value here, to negative 5. So it's not actually a solution. Even though it does intersect with the branch, it's not a solution to our problem. And that's why we always have to do our check at the end. So there is only one solution to this problem, which is negative 5/3. So at the end of the problem, after we've done our checks, you should really make your answer clear. X equals negative 5/3. There we go. Okay, D. Let's see if we can answer this one. We have two separate absolute value functions here. a little bit more complicated, right? But if you look closely, it's actually not too different because 3x minus 4 and 9x minus 2 actually share something in common. Can you see it? Can we factor something out of that second one? We can, right? There's a common factor of 3 in both of those terms, right? So what happens if I factor to 3? First of all, am I allowed to do this? Look at that. Am I allowed to do that? Well, by pulling out a 3, we're not actually changing the positive or negative sign of what's in here. We're basically keeping it the same, right? We're just dividing everything by 3. So we're not changing anything. So yes, we're allowed to treat the absolute value function like brackets here and just pull out a 3. Furthermore, we now have two things. So there's actually two terms in this, but they're both common terms. They're the same thing. So it's like we say we have 1 3x minus 4 is here, and 3 3x minus 4 is there. So we're just going to add those like terms. So we have 4, the absolute value of 3x minus 4 equals 12x. There we go. So we just collect our like terms, and now we have a function that looks very similar, or an equation that looks very similar to the previous question. So pause the video here. See if you can find all the possible solutions to this question. When you're done, unpause and see if you can, and see if your answer matches up. Okay, so here's what happened after I did the work. I split this up, absolute value of 3x minus 4 equals 3x into two cases, where 3x minus 4 is greater than 0 and where it's less than 0. And we see the negative case is very simple. It comes out to 2/3. I checked, and when you check, it turns out that that is a solution. So 2/3 is a solution. But what's more interesting is what happens on the positive side. Solving this equation gave me something really weird. It gave me that 0 equals 4. Is that true? Did we just break math? 0 definitely does not equal 4. So let's just backtrack here about what happened. So I plugged in positive 3x minus 4, and I solved. So really, I'm gonna skip this actually. If we go back here, that 3x minus 4, really if I bring this 3x to the other side and this 4 to the other side, it's gonna look like this. 3x minus 3x equals 4. Or 3 minus 3 is just gonna be 0. So it's like we're saying 0x equals 4. Now the question is there anything that we can plug in for x here to make this equation true? No, there isn't, right? No matter what we plug in for x, it's going to be times 0. So it's going to give us 0. So it's impossible to get that value to 4. So it's not that we broke math. 0 does not equal 4. All it's telling us is that there are no solutions. There's no possible answers to this, at least this part of the equation. So in the positive branch of the absolute value function, there's no solution. So stepping back for a second, without throwing in decimals, let's just think about it for a second. It says, so just doing a quick sketch actually, it says that there's an intersection point. We know the absolute value function is going to look something, I don't know, something like this, right? I'm just drawing a random function. We know that there's a point of intersection in the negative root, right? So this negative part here is going to have some point of intersection of, say, I don't know, up here. But what does it mean for there to be no solution? Or this 0x equals 4? Essentially what that's telling us is that there's going to be no solution, no point of intersection between this line here and this line here, the line that's represented by 3x and this line here. So essentially what that means is that those two lines are parallel. So this line here and this line here are actually parallel. When we get nonsense like this in a solution for a question, it essentially means that there's no point of intersection between those two lines because they are parallel. That's the only way two lines aren't going to meet somewhere. So don't fret if you get something like this. You didn't break math. You just found, or you're just trying to find the solution between two things that are parallel, which clearly there's not going to be any solutions to that.